Most programming languages ask a proposition to be true or false. That is a useful simplification, but it can hide two situations that matter in reasoning systems. There may not be enough evidence to decide, or the evidence may conflict. Semantic is an experimental language platform built around making those situations explicit. Its repository describes the platform as deterministic and verifier first, with a native four-state logic domain. That framing matters. This is not a claim that Semantic is a finished general-purpose language, and it is not a promise of production readiness. It is a specific architecture for programs where uncertainty and contradiction should remain visible instead of being silently collapsed. In this video, we will follow one real program from source code, through analysis and a version artifact, into a verifier gate, and finally into admitted deterministic execution. Semantic calls its four-state type quad. The states are N, F, T, and S. N means there is not enough evidence. F means false. T means true. S means conflicting evidence. A useful way to see the model is as two evidence bits. One bit records falsity evidence, the other records truth evidence. 0 and 0 gives N. Neither side has support. 1 and 0 gives F. 0 and 1 gives T. 1 and 1 gives S, where both sides are present. The repository's canonical encoding writes those states as 00, 01, 10, and 11. This is why quad is not just a strangely named Boolean. It must not be treated as false, and S must not be treated as true or false without an explicit policy. The state carries information that ordinary binary control would throw away. Here is the canonical rule state example used in our recorded demonstration. It defines a decision context with a camera state, an override state, and a Boolean readiness flag. The decide function returns a result containing a quad. A strict override wins first. An unknown camera becomes an explicit error state. If the system is ready, the function returns T. Otherwise, it can return conflict S. Main construct of context matches the result and asserts the expected verdict. The important point is not the business rule. It is that the source keeps unknown and conflict visible all the way through the decision. We did not invent this code for the animation. It comes from the canonical examples at the exact commit shown on screen, and the same file was checked, compiled, verified, executed, and disassembled before it was admitted into the video. The first stages look familiar. Source enters a frontend, then semantic analysis. Parsing establishes structure. Semantic analysis resolves names, checks types, and determines whether the program fits the admitted source surface. The public documentation groups syntax, types, source semantics, diagnostics, and modules in the current core specification bundle, which is still labeled draft version 0. That status label is important. An implemented compiler path and a final language specification are different claims. For the qualified practical contour, the repository documents an end-to-end route from source, through semantic analysis and intermediate representation, to SemCode, the verifier, and the VM. A source check is useful feedback, but it is not the final trust decision. The onboarding order is deliberately staged. Check the source, compile the artifact, verify the artifact, and only then run admitted code. After semantic analysis, Semantic lowers the program into deterministic intermediate representation. From there, the emitter creates SemCode, a version.smc artifact. Think of SemCode as the concrete handoff between construction and admission. Source syntax can be convenient and expressive. The verifier needs a bounded artifact with explicit sections, functions, operands, jumps, capabilities, and a declared header family. The canonical documentation shows the compiler producing a .smc file before verification and execution. In our demo, the artifact is 654 bytes and identifies itself as SemCode 0, Epic 0.1. But an artifact existing on current main does not automatically make every feature it contains part of the stable promise. Semantics status model separates implementation from release maturity. The artifact is therefore both executable material and an accountability boundary. It is the exact thing the next stage will either reject or admit. The verifier is the center of the architecture. Current checks cover the header and supported version, function and section integrity, opcode and operand validity, jump and call targets, register budgets, and consistency between capabilities and the instructions that use them. Unknown, unsupported, malformed, or structurally invalid instruction streams are rejected before a successful VM path. The gate has two honest outcomes: reject with deterministic diagnostic context, or admit by producing a verified token for trusted execution. Compilation success does not waive this step. Even an artifact emitted by the project's own compiler still crosses the verifier boundary. That is what verifier first means here. The compiler constructs a candidate program. The verifier independently decides whether the candidate satisfies the executable contract. The VM is not asked to discover malformed structure while already running it, and VM execution never substitutes for admission. Once admitted, SemCode enters the semantic virtual machine. The VM is register-oriented, manages call frames, enforces runtime quotas, and reports failures explicitly. Determinism is defined against the same verified artifact, execution configuration, and entry function. The broader rerun invariant also includes the same capability context and input stream. This does not mean every admitted program must succeed. An admitted program can still exhaust a quota, fail an assertion, or encounter another defined runtime trap. What matters is the boundary between failure classes. A verifier rejection says the artifact was not admitted. A runtime trap says an admitted execution encountered a defined failure. Keeping those categories separate makes traces and tests easier to reason about. Given the same inputs to the execution contract, the VM should not invent a different result merely because the host machine happens to schedule work differently. Pure computation can stay inside the VM. External effects cross a separate boundary owned by Prometheus-facing capability policy. The documented narrow path routes a host effect instruction through the ABI host interface and a capability check. If the required capability is missing, the effect is denied before the host call happens. Denial is not just a false Boolean. It is an explicit report with the capability, host call identity, manifest metadata, denial code, and a readable message. The current main branch also contains a narrow print text path. Its documented flow moves from verified SemCode to a controlled VM observation event, then through a capability gate, an audit decision, and finally a CLI rendering envelope. That should not be misread as unrestricted standard output, files, input, networking, or a general host ABI. The capability boundary is where deterministic computation asks for a specifically authorized interaction with the outside world. Now the actual command line. These are deterministic terminal animations generated from captured process records, not a hand-edited screen recording. First, SMC check reports 0 warnings and 0 scheduled loss. Next, compile writes the 654-byte artifact. Verify accepts 2 functions under the SemCode 0 header and epic 0.1. Run SMC exits successfully with no fabricated console output. The example proves its result through an assertion. Finally, SVM disassemble exposes the artifact's real instruction stream. Load quad constants, construct a record, call the decision function, inspect the result tag, compare the verdict, assert, and return. Every record stores the command, standard output, standard error, exit code, duration, and semantic commit. Local usernames and private paths are redacted before rendering, but the semantic content and exit results are preserved. Semantics repository deliberately separates 4 layers of truth. Published stable is the versioned public baseline, currently version 1.1.1. Qualified limited release is a narrow, practical contour supported by a completed evidence cycle. Landed on main means code exists and may even have benchmark positive evidence, but has not been promoted into the stable or qualified promise. Out-of-scope names surfaces intentionally excluded from the current contract. The verified source-to-VM path used here belongs to the qualified contour. Current main also contains wider work, including additional practical language and application surfaces, without silently making those stable. Broader executable modules, full command line I/O, the user interface layer, and generalized iterable dispatch remain outside the current qualified contour. So the honest description is active research and limited qualification, not a finished general-purpose language and not production-ready software. The architectural value is separation of responsibility. The frontend explains source. Semantic analysis decides whether that source is meaningful. IR and SemCode make the executable candidate explicit. The verifier owns admission. The VM owns deterministic execution of admitted code. Capability policy owns permission to cross in a host effects. Each boundary narrows what the next component is allowed to assume. That is useful for language research because a new source feature does not have to become a new trust shortcut. It is useful for systems work because malformed artifacts, runtime traps, and denied effects remain different events. And it is useful for reasoning programs because N and S can remain visible rather than disappearing into a Boolean convention. This architecture does not automatically prove application correctness or host safety. It creates named places where evidence, admission, execution, and external authority can be checked independently. Semantic starts with a distinctive idea. Truth may be unknown or conflicted, not only true or false. It carries that idea through a stage platform. .sm source passes through frontend and semantic analysis, deterministic IR, and a version SemCode artifact. The verifier either rejects the artifact or turns it into an admitted token. The deterministic VM executes that admitted program. Optional external effects cross a separate capability control boundary. The live repository supports this path, and our recorded example exercises it at the commit shown here. Just keep the maturity labels attached. Stable publication, qualified limited release, current main work, and research direction are not interchangeable. That honesty is part of the system's design. Semantic is not presented here as a finished universal language. It is a concrete verifier-first platform for exploring explicit for-state reasoning and controlled execution.